Today, we are going to begin talking about the concept of inductance and the circuit elements inductors. So let's start by defining what the first one that I am going to draw is what we're going to call a solenoidal inductor. So in a solenoidal inductor, we are going to have a cylinder of material. Like so. We're going to call this cylinder our core material. Our core material could be air, but more likely it will be some type of ferromagnetic material. So some type of iron or iron alloy. Okay. Around this core, we are going to wrap a wire. Like so. When this wire carries a steady current I, the coil will have a constant magnetic flux flowing through it. So these lines in this color are our magnetic flux lines. And our coil has some number, let's call it N, turns. And so what that magnetic flux is inside the coil is a form of temporary energy storage. So if we pass a current, we cause some amount of magnetic flux to be kind of compressed inside of that coil. And then when we turn off that current, the magnetic flux is going to induce a current in response, which will release energy back into the system. So this is an example of a solenoidal inductor. The other type of inductor that you may see, and if you ever crack open the case of one of your computers, I guarantee you'll see several of these, is the toroidal inductor. So for a toroidal inductor, that's effectively, bear with me because this one is a little bit harder to draw. A donut, where we wrap a wire around said donut. Like so. And again, if we pass some steady current I into our coil, we will observe magnetic flux lines circulating around our toroid like so. And this stored magnetic flux is, once again, the energy storage mechanism for the device. Okay? So how we're going to classify how an inductor behaves is going to take a very small amount of physics. Okay? So if we have a current carrying wire, so let me write down toroidal inductor here. So if we have a wire and it's carrying a current I, what we will observe is a magnetic field that wraps around the wire. And it wraps around the wire using what's called the right-hand rule. Like so. Anytime we have current flowing through a wire, we have some magnetic or E field that's associated with that current. Well, in an inductor, as I've mentioned previously, we store that electric field. So the magnetic flux that is inside the core, we write the word "the" better. So the magnetic flux inside the core is concentrated which, hold on. Concentrated by coiling the wire, which is what we have observed in both of our inductors. And allows the inductor to store energy. The flux, magnetic flux, inside the coil is dependent on the amount of current passing through the coil. As magnetic flux which has a symbol of phi b is equal to the inductance of the coil, L, multiplied by the current carried in the coil, I. So what inductance is it's the ratio of the change in magnetic flux of a circuit element due to a corresponding change. Sorry, I don't know why my screen zoomed in. An electric current. Okay, so let's talk about this definition here really quickly. Okay, so what this means is that the inductance of a the inductance of an electrical component is really a measure of how well it resists changes in electrical current. Okay. How many of you guys have ever used a hair dryer and then unplugged it and seen sparks? Well, if you have, it's because the hair dryer uses a small induction motor inside of it to power its fan. And when you abruptly change the current flowing through that motor by disconnecting the device, the large inductance of the coil inside the hair dryer tries to keep that current flowing. And its drive to keep that current flowing is so large that it will literally ionize the air particles across the terminals of the hair dryer in order to keep the current constant for a few seconds. Okay. So inductance L is the ratio of magnetic flux to current. And magnetic flux has units of Webers. Current has units of amperes. And I know that the overwhelming majority of you probably aren't familiar with the units of Webers. A Weber is nothing more than a volt second. So we have a volt second over ampere, and we call this 1 Henry. So the Henry is the unit of inductance. An alternative definition for inductance is the tendency of an electrical conductor to oppose a change in the electrical current flowing through it. This relationship is described by Faraday's law. So Faraday's law says E, the electromotive force, is equal to negative the change in magnetic flux with respect to time. Okay. This electromotive force E is really just a fancy word to describe voltage. I know your physics professors would literally hate me for saying that, but voltage is an example of an electromotive force. Okay, not all voltages are electromotive forces, but not all electromotive forces are voltages, I guess would be the way to put it succinctly. Okay. So this Faraday's law of induction is actually going to describe how our inductors behave in a circuit, because we have a voltage that is appearing due to a change in magnetic flux, and we know that the magnetic flux is in turn dependent on current. Okay. So we can rewrite this in circuits form as VL, the voltage drop across an inductor, is equal to negative d phi b of t by dt, or L times DIL by dt. This equation is an important one because it gives us a current voltage relationship for our inductor. Okay. So before we move along and analyze this equation a little bit, I need to introduce the schematic symbol for an inductor, which is this guy right here. So we represent an inductor by a coil of wire, where the inductor has some inductance L, and it obeys the passive sign convention such that if there is a voltage drop VL over the inductor with a positive polarity on the left, if current IL is flowing into the positive polarity terminal, then our inductor is absorbing power. Okay. And then we use this relationship to describe how IL and VL relate to each other. Okay. Now, this equation is very interesting because it actually tells us two very important things about how an inductor behaves. So let's address the first one. What voltage appears across an inductor if it carries a DC current? Okay. So from our equation, we know that the voltage that appears across the terminals of an inductor is proportional to the change in the current flowing through the inductor. So if an inductor is carrying a DC current or a non-changing current, then the voltage drop across the inductor has to be 0 volts. So in a DC circuit, an inductor behaves like a short circuit, just a piece of wire. Okay. Now, let's use a little math and look at a slightly different interpretation of what's going on here. Okay. So let's say that I'm applying a particular current waveform to an inductor. Let's say that my current does something like, let's do it like this. Like this. Just for the sake of argument, let's call this 10 amps. Let's call this 2 seconds. Let's call this 7 seconds, this 9 seconds, this over here is 0 seconds. On the right, what we're going to do is we're going to figure out what voltage would appear across our inductor as a function of time. So this is going to be VL of t. So if we have an inductor, let's put it over here, of 1 Henry, here's VL and here's IL. So if we have an inductor of 1 Henry and we pass that current waveform that I've outlined in red through that inductor, we should observe that a voltage is going to appear across the inductor. right? So since VL is given by L times DIL by dt, we can infer that whenever the inductor current is changing is when we'll actually see a voltage. So in this region right here, where t is between 0 seconds and 2 seconds, our current is changing. And the change has a slope that is m is equal to 5 amps per second, right? Because we have a total change of 10 amps over a total duration of 2 seconds. So if we have that slope, 5 amps per second, and we multiply it by our 1 Henry inductor value, where a Henry is a volt amp per second, what we'll find is that we will carry a voltage of 5 volts across the inductor terminals for 0 to 2 seconds. So here's 5 volts, here's 0 seconds, here's 2 seconds. Over the time interval from 2 seconds to 7 seconds, since the current is constant, the voltage drop across the inductor will be 0. So if here is 7 seconds, we're going to have a 0 voltage over that interval. And then here, our slope is negative 5 amps per second. And so we're going to see that our voltage will now become negative. For 2 seconds, like so. Okay. So this is how an inductor processes a changing current, all right? The voltage drop across the inductor is proportional to the change in the current. Well, what if we sped up the duration of how quickly the current changes? So if this is IL of t, and now our current waveform looks like this. What we should expect to happen is that if our current changes twice as fast, we should get twice the voltage. So in this case, this would be 10 volts. And negative 10 volts. If we take this to an extreme, where, excuse me, this should be red. The current through our inductor abruptly changes. So at 0 at the instant before t is equal to 2 seconds, and then it is 10 amps at the instant after t is equal to 2 seconds. And then it stays 10 amps until we hit 7 seconds before dropping instantaneously down to 0 the instant after t is equal to 7 seconds. What's going to happen to our voltage? Well, it depends on what the slope of our change is, right? In this case, we have an instantaneous change in the current. And so what that's going to cause to happen is that we will have impulses on our voltage waveform. So we would get an infinitely large positive voltage spike when our current jumped up from 0 to 10 amps. And we'd get an infinitely large negative voltage spike when our current jumps down from 10 amps to 0 amps. Unfortunately, we can't have an infinite amount of voltage created, because an infinite amount of voltage would require an infinite amount of energy transfer in an infinitesimal amount of time. So from this, we can say the current flowing through an inductor cannot, change abruptly. This is another fundamental rule of how inductors behave, and we are going to use this rule a whole heck of a lot later on next week when we start talking about the concept of transient analysis of RL circuits. Okay. All right, so just to recap what we've covered thus far, we have developed this first equation that says the voltage drop across an inductor is equal to L, the inductor value, multiplied by the change in the current that's flowing through the inductor. From this mathematical relationship, we have observed two things about how inductors behave. In a DC circuit, an inductor behaves like a short circuit. And in an AC circuit, or one where the voltages and currents aren't constant, we have observed that the current that flows through an inductor cannot change instantaneously, or it cannot change abruptly, meaning it can't be, let's say, 5 amps and then also 10 amps at the same point in time, okay? What we're going to do now is we're going to mathematically manipulate that first equation to develop our second relationship. So I'm going to rewrite it down here. VL of t is equal to L di by dt. And now I'm just going to multiply both sides by dt. So that's going to give me VL dt is equal to L DIL. I'm going to take this L right here and put it over here like this. So I've divided both sides by a factor of L. And now I'm going to integrate both sides. So if I take the integral of this side and the integral of this side, what I get is the current flowing through an inductor as a function of time is equal to 1 over L times the integral from negative infinity to t of VL of t prime dt prime, where t prime here is just a dummy variable for time. And I can expand this a little bit by saying we're going to have the integral, or 1 over L times the integral from t naught to t, VL of t prime dt prime plus IL at t naught. So let's interpret this mathematical expression here. And I'm going to put a box around it because this is our second big equation that we need to know. So what this equation says is that the current flowing through an inductor is equal to 1 over L times the integral of the voltage drop across the inductor plus whatever value the current had when we started integrating. So effectively, an inductor has a little bit of memory in that its present value of current depends on the past value of the current, okay? This is an important quantity. We'll see the exact same thing, or actually we'll see a very similar thing when we look at capacitors in our next class meeting, okay? So if we take those two equations, we can develop a relationship for power. So the power absorbed by an inductor will, by definition, be the current flowing through the inductor multiplied by the voltage drop across the inductor. If we use equation 1 to express the voltage drop across the inductor in terms of the current flowing through the inductor, this becomes L I by di by dt. So make sure that you can see that that's I of L. There we go. So this is our power relationship. This is equation number 3 regarding the behavior of an inductor. And lastly, we're going to look at the energy stored by an inductor. Energy, W, is the integral of power. So we're going to determine the energy stored by an inductor by setting our boundaries of integration from negative infinity to t, the time that we're interested in, and that's going to cause us to write this as PL as a function of t prime and dt prime. Okay. Well, if I substitute in the relationship for power that I just got, this is going to look like L IL of t prime DIL of t prime by dt prime dt prime. Okay. So this dt prime and this dt prime cancel each other out. And what I'll have is the integral from whatever IL was at negative infinity to whatever IL is at the time I'm interested in of L IL of t DIL of t, And if we consider that there was no energy, or excuse me, no current flowing through the inductor at t is equal to negative infinity, the result of this integration gives us the energy stored by an inductor is simply 1/2 L times IL squared. This is our fourth equation. All right, so before we move along and work an example problem here that utilizes these relationships, I want to inform you of something. Okay? I have boxed 4 equations here regarding the behavior of inductors. The first expresses the voltage, so you use it to find the voltage when you know what the current is. The second equation allows you to find the current when you know what the voltage is. The third equation allows you to determine the power absorbed by an inductor. And the fourth equation allows you to determine the energy absorbed by an inductor. For your exam, I expect you to know all 4 of these. You are not allowed an equation sheet, okay? So I have made a point to box them in and bring your attention to them. It is very, very critical that you get these relationships by heart. When we cover capacitors next Tuesday, I believe, we will develop 4 almost identical relationships. I will then show you a trick that will allow you to swap back and forth between the capacitor relationships and the inductor relationships. All right. Let's look at an example problem. So let's say that I have an inductor and its inductance value is 250 millihenries. The voltage drop of the inductor has this polarity, and the current flowing through the inductor has this polarity. If VL of t is equal to 0 volts for t is less than 0 seconds, and it is equal to 5e to the negative alpha t volts for t is greater than or equal to 0 seconds. And out here, I'm just going to say specifically that alpha is equal to 4 per second. What is the energy stored by the inductor as a function of time? Okay. So how we would approach a problem like this is first by looking at what we're asked for, right? So we know from equation 4 that the energy stored by an inductor is 1/2 L times the square of the inductor current. 1/2 is a constant. L was given to us, but we don't know what IL is. So that means we're going to have to solve for IL. IL is given by the 1/L times the integral from T0 to T of VL T prime dt prime plus IL at T naught, okay? So we weren't given a value for IL at T naught. So in this particular problem, we are going to assume that this term goes to 0. In some homework problems, you might be told that the current flowing through in the inductor at a specific time is equal to some value. You would just plug that into your equation. Okay? So excuse me. What we are going to do here is we're now going to solve for our inductor current. And I want us to pay close attention to the units here, because the overwhelming majority of the problems that you guys are going to face in your homeworks, in your exams and stuff like that is going to be dealing with the units. The calculus that's involved here is fairly straightforward, right? So we have 1 over L. So that's 1 over 250 millihenries times the integral from 0 to T of 5e to the minus 4t volts, T prime here, sorry, dt prime. So what I'm going to do first is let's break down this 1 over 250 millihenries into its constituent units, okay? So we're going to have 1 over 250 times 10 to the minus 3. A Henry is a volt second per ampere. Now I'm going to take 5 volts out of my integral expression. And we can see that the units of volts here cancel out the units of volts here. Then we're going to have the integral from 0 to T of e to the negative 4t prime dt prime. How do we take the integral of an exponential function? Okay, we're going to be dealing with exponential functions an awful lot in this class. So as a very quick reminder, if we have a function e to the alpha t, the derivative of e to the alpha t is alpha e to the alpha t. The integral of e to the alpha t dt is 1 over alpha e to the alpha t plus c. Okay. So in this case, my alpha quantity is -4 per second. So when I perform this integration, I'm going to have 5 amps over 250 times 10 to the minus 3 seconds. I pull out my 1 over alpha factor. So that's going to be 1 over -4 per second. Notice now that I have seconds in the denominator and per seconds in the denominator, so those units cancel each other out. And then I'm going to have e to the minus 4t prime evaluated at 0 and t. So let's play around with these numbers real quick, okay? So I have 5 amps in the numerator, and then I have 250 times 10 to the minus 3 times a factor of -4. 250 times 10 to the minus 3 is 0.25 times 4 gives me 1. So this is going to look like -5 amps multiplied by e to the minus 4t minus e to the minus 4 times 0. E to the minus 4 times 0 looks like 1. And so my inductor current, IL of t, is going to look like 5 minus 5 e to the -4t amperes. From here, we can get back to our inductor energy. So this is going to be 1/2 L times 5 minus 5 e to the minus 4t amperes quantity squared, which is going to look like 1/2 times 250 millihenries times, so 5 times 5 is going to give me 25 amps squared, and then I'm going to have 5 times -5 e to the minus 4t, so that's going to look like minus 25 e to the minus 4t amps squared. Then I'm going to have another of that same thing, -25 e to the minus 4t amps squared. And then lastly, I'm going to multiply -5 e to the minus 4t times -5 e to the minus 4t, which is going to look like plus 25 e to the minus 8t amps squared. So I have 1/2 times effectively 1/4. So let's spell this out directly. 250 millihenries is 1/4 of a volt second per ampere times 25 amps squared minus 50 e to the minus 4t amps squared plus 25 e to the minus 8t amps squared, like so. Now let's look at these units, okay? So amp here is going to cancel one of these amps on all of these terms. So I'm going to have volts times seconds times amps. Well, a volt times an amp is a watt, and a watt times a second is a joule. So we are correctly doing energy. I have a factor of 1/2 times 1/4, so that looks like 1/8. So this is going to be 25/8 minus 50/8, which is going to look like 25/4 e to the minus 4t plus 25/8 e to the minus 8t. So that's our energy stored by our inductor. All right. The last thing that I want to talk about today, I'm sure I'm boring you guys to death, is how we combine inductors in circuits that contain multiple inductors. So let's start by looking at inductors in series. Okay. So let's say that we have a combination of inductors. Let's call this L1. This is L2. And this is Ln. Each inductor will have a voltage drop across it, VL1 of t, VL2 of t, all the way out to VLN of t. And all of the inductors will be carrying the same current, which I'm going to call I of t. And let's say, for the sake of argument, that there is just some voltage V of t across all of these inductors in series. If we apply Kirchhoff's voltage law around the loop, we find that our total voltage V of t is simply the sum of all of our voltage drops across each individual inductor. So VL1 of t plus VL2 of t all the way out to VLN t. Now I'm going to express all of those inductor voltages in terms of my inductor current, I of t. So that's going to look like L1 times di by dt plus L2 by di by dt all the way out to Ln di by dt. All of these terms contain a common factor of di by dt. So that means we can say that our voltage is L1 plus L2 all the way out to L sub n di by dt, or LEQ di by dt, where LEQ is simply L1 plus L2 all the way out to L sub n. So in short, inductors in series combine like resistors in series. Now let's look at a combination of parallel inductances. So let's say that we have several inductors connected in parallel. Here's L1. Here's L2. Here's L sub n. We have some total amount of current, I of t, flowing into this network containing all of our parallel inductors. Since all of these inductors are in parallel, they have the same voltage drop across them, and our total current I of t is going to split and flow through individual inductors so that we'll have IL1 of t, IL2 of t, all the way out to ILN of t, like so. If I apply Kirchhoff's current law, I can find that I of t is equal to IL1 of t plus IL2 of t all the way out to ILN of t. I can express all of those currents in terms of the common voltage V of t. So that's going to look like 1 over L1 times the integral from negative infinity to t of V of t prime dt prime plus 1 over L2 times the integral from negative infinity to t of V of t prime dt prime all the way out to 1 over L3 times the integral from negative infinity to t, ln, my apologies, V of t prime dt prime. And since all of these components have that same integral, I could say this is 1 over L1 plus 1 over L2 plus all the way out to 1 over L sub n times the integral from negative infinity to t v t prime dt prime, or 1 over LEQ, integral from negative infinity to t vt prime dt prime, where LEQ is 1 over L1 plus 1 over L2 all the way out to 1 over L sub n to the minus 1 power. In other words, inductors in parallel combine like resistors in parallel. So the calculus-based relationships that these circuit elements obey does not interfere with the way that we do our combinations as compared to resistors. All right, that's enough out of me for today. I will continue to hang out in Zoom if anybody has any questions. If not, I will see you guys next Tuesday. Please have a happy and safe Independence Day weekend.